Max Planck, born on the 23rd of April 1858 in the vibrant city of Kiel, Germany, came into a world that was undergoing monumental change. His family, steeped in academic tradition, laid the foundation for his future intellectual pursuits. His father, Johann Julius Wilhelm Planck, was a distinguished professor of law at the University of Kiel, while his mother, Emma, was the daughter of a prominent judge. It was within this environment of intellectual rigor and academic excellence that Max Planck's early years were shaped. Planck's early life was marked by a deep appreciation for learning, instilled by his parents. From an early age, he exhibited an exceptional curiosity about the world around him. His family recognized this and encouraged him to explore various fields of knowledge. His environment in Kiel, a city known for its academic and cultural richness, provided him with a fertile ground to nurture his intellectual curiosity. However, it wasn't just the academic environment that shaped him. The emotional and intellectual support of his family played an equally important role in his development. This early exposure to a scholarly atmosphere set the stage for his later achievements in the world of physics. At the age of 17, Max Planck left his hometown to pursue higher education at the University of Munich. This was a crucial turning point in his life, marking the beginning of his formal academic journey. The transition from his hometown to a larger academic environment was not only a geographical move, but also an intellectual leap. Munich, with its vibrant intellectual community and world-class faculty, was an ideal place for a young, ambitious student like Planck to immerse himself in the study of physics and mathematics. Planck's academic interests, however, were not immediately focused on the field of physics. Initially, he enrolled in the University of Munich with the intention of studying engineering, a subject he believed would offer practical applications of scientific principles. However, it was during his time in Munich that he became increasingly drawn to theoretical physics. This shift in focus was partly due to the influence of his professors, particularly Philipp von Jolly, a renowned professor of physics. Von Jolly's lectures on the laws of thermodynamics and the nature of energy deeply impacted Planck and sparked a lifelong interest in the field. Planck's decision to study physics was further solidified during his time at Munich, where he encountered the works of leading physicists such as Hermann von Helmholtz and Gustav Kirchhoff. These towering figures in the field, who were shaping the future of thermodynamics and electromagnetic theory, profoundly influenced Planck's thinking. He was particularly drawn to their work on the conservation of energy and the development of the laws governing heat and light. This exposure to cutting-edge physics during his early academic years laid the groundwork for Planck's future contributions to the field. In 1879, after completing his studies in Munich, Planck moved to the University of Berlin to continue his academic journey. The move to Berlin was a significant step in his intellectual growth. Berlin, at the time, was a thriving center of scientific thought, home to some of the greatest minds in physics and mathematics. It was here that Planck came into contact with the works of prominent scientists like Albert A. Michelson and Hermann von Helmholtz. These encounters broadened his perspective on the scientific world and deepened his commitment to the pursuit of knowledge. In Berlin, Planck was able to engage in a more specialized study of physics, particularly in the area of thermodynamics. He worked closely with his mentor, Heinrich von Wurtz, whose guidance further honed Planck's analytical and experimental skills. It was under von Wurtz's mentorship that Planck began to develop his own approach to scientific problems, one that combined both theoretical reasoning and empirical evidence. This method of investigation would become a hallmark of Planck's future work, as he sought to bridge the gap between abstract theory and observable phenomena. Throughout these formative years, Planck's approach to physics was shaped by his belief in the power of mathematical precision and logical rigor. He was deeply influenced by the German tradition of exact science, which emphasized the importance of mathematical models in explaining natural phenomena. This dedication to mathematical reasoning would prove to be a crucial element in his later groundbreaking work in quantum mechanics. Despite the intellectual excitement of Berlin, Planck's early academic years were not without personal struggles. His first academic endeavor, a dissertation on the second law of thermodynamics, was met with mixed reactions. While the work was not groundbreaking, it served as a vital stepping stone for Planck's academic development. The feedback he received from his professors at the University of Berlin was constructive and challenged him to think more deeply about the questions he was pursuing. Rather than being discouraged by the criticism, Planck used it to refine his approach and deepen his commitment to his academic studies. His time in Berlin also exposed him to a wide array of scientific ideas, some of which were in direct contrast to the established theories of the time. The work of James Clerk Maxwell and Lord Kelvin on electromagnetism and thermodynamics offered new avenues of exploration for young physicists, including Planck. These ideas would go on to influence his thinking in the years to come, providing him with the tools to challenge conventional wisdom and push the boundaries of scientific understanding. By the end of the 1880 seconds, Planck had firmly established himself as a promising young physicist with a unique perspective on the nature of energy and matter. He had already made several contributions to the field of thermodynamics and had become increasingly interested in the emerging field of quantum theory. It was during this period of intellectual ferment that Planck's most significant academic achievement took shape. His early academic years, marked by rigorous study, intellectual curiosity, and the guidance of influential mentors, laid the groundwork for the revolutionary work he would go on to do in the early 20th century. In retrospect, Planck's early academic years were not just a time of learning and intellectual development, but also a period of self-discovery. He emerged from these years not only as a brilliant student but also as a thinker, ready to challenge existing scientific paradigms. His academic journey was shaped by the people he met, the ideas he encountered, and the questions he sought to answer. These early experiences would later fuel his groundbreaking work in the field of quantum physics, earning him a place among the greatest scientific minds in history. Max Planck's early academic years were not just about acquiring knowledge, but also about forging the intellectual foundations that would support his future revolutionary contributions to science. His years at the University of Munich and later at the University of Berlin were marked by rigorous learning, intense curiosity, and the cultivation of a deep love for theoretical physics. However, these years also represented the period in which Planck's intellectual journey took a more defined direction, influenced by several key academic and personal factors that would shape his groundbreaking work later in life. In Berlin, Planck's understanding of physics matured significantly. The city was home to some of the greatest scientific minds of the era. One of the most significant influences during this period was Planck's engagement with the work of leading physicists, such as Hermann von Helmholtz, who was renowned for his work on thermodynamics, and Gustav Kirchhoff, whose contributions to the theory of radiation and the laws of heat would directly inform Planck's own research. Helmholtz, in particular, left a deep mark on Planck, as his ideas about energy conservation and the laws of nature inspired Planck's belief in the universality and precision of natural laws. This exposure to the works of these distinguished scientists would guide Planck's own theoretical explorations into the mysteries of the physical world. During his time in Berlin, Planck's passion for thermodynamics and statistical mechanics grew. He immersed himself in understanding the laws governing heat, energy, and matter. Thermodynamics was the central area of focus for Planck, who was captivated by the concept of energy transformations. At that time, classical physics was struggling to explain some phenomena related to the behavior of energy, particularly in systems at the atomic and molecular scale. Planck sought to reconcile these inconsistencies and it was during this period that he developed a deep understanding of the gaps in the existing theories of the time. While Planck was heavily influenced by the scientific community in Berlin, it was his growing frustration with the limitations of classical thermodynamics that pushed him to think outside the box. He began to see that the classical theories of the 19th century were not sufficient to explain the phenomena he was investigating. This realization would ultimately lead him to explore the idea of quantization of energy, a theory that would revolutionize physics and form the foundation of quantum mechanics. But this was still some years ahead. For now, Planck was grappling with the basic principles of thermodynamics, developing a nuanced understanding of the second law and its implications for the behavior of energy. The importance of mentorship during Planck's academic years cannot be overstated. In Berlin, Planck was fortunate to work under some of the leading figures in physics, one of whom was Heinrich von Wurtz, a mentor who helped Planck refine his approach to scientific inquiry. Wurtz's rigorous scientific methods and emphasis on experimental evidence profoundly shaped Planck's approach to research. Planck was not content to simply accept theoretical models. He wanted them to be substantiated by experimental data and to be grounded in observable phenomena. This commitment to empirical evidence would become a hallmark of Planck's later work, especially when he made the leap into the development of quantum theory. At the time, German universities were known for their precise and detailed approach to science, and this system of intellectual rigor was a perfect fit for Planck's methodical nature. The environment of Berlin provided him with access to an impressive array of scientific literature, experimental data, and a network of like-minded scholars, all of which encouraged him to push the boundaries of traditional thought. Planck's decision to pursue a career in academia was solidified during his time in Berlin. He realized that his true calling lay in not just studying science, but also in contributing to it by developing new theories, asking new questions, and challenging the status quo. This realization, however, would not have come to fruition without his early academic struggles and the mentorship he received from those around him. Planck's exposure to the scientific community in Berlin also helped to shape his understanding of the scientific method. The rigorous approach to research and the importance of critical thinking that he encountered during his time in Berlin instilled in him the belief that scientific progress depended on the ability to question assumptions, rigorously test hypotheses, and constantly re-evaluate existing models. It was in Berlin that Planck began to develop a scientific philosophy that would guide him throughout his career. He believed that science should be an unrelenting quest for truth, a journey that involved both questioning old ideas and rigorously testing new ones. Planck's academic journey in Berlin was also marked by his growing interest in the broader implications of his research. He began to see his work not as a solitary pursuit but as part of a larger scientific endeavor. The intellectual environment of Berlin, where scientists constantly exchanged ideas and challenged each other's thinking, made Planck realize that his contributions were part of a much larger dialogue in the scientific community. This awareness deepened his sense of responsibility to advance the field of physics and to contribute something meaningful to human understanding. The intellectual ferment in Berlin during Planck's years, there was also a period of personal growth. Planck's exposure to various scientific ideas, both theoretical and experimental, allowed him to broaden his horizons. He was not content with simply learning from others. He sought to integrate and synthesize the different threads of scientific thought into his own approach. Planck's ability to synthesize the work of his predecessors and combine it with his own ideas would later enable him to make groundbreaking contributions to physics, including his work on black-body radiation and the development of quantum theory. Despite the challenges, doubts, and periods of uncertainty he faced in his early academic years, Planck's time in Berlin helped him realize his potential as a physicist. His ability to remain focused, even in the face of criticism, and his relentless pursuit of deeper understanding set him apart from his peers. Planck's early academic journey was not without its struggles, but it was precisely these struggles that forged the intellectual resilience he would need to tackle the complexities of quantum mechanics. By the time Planck left Berlin and embarked on his career as a professor, he had already established himself as a promising young physicist with a unique perspective on energy and matter. His academic years in Berlin laid the intellectual foundation for the revolutionary ideas he would later develop. His time spent learning from the great minds of his era, grappling with the mysteries of thermodynamics, and engaging in intense intellectual debate would propel him toward a future where he would make contributions that would forever change the course of physics. Planck's early academic experiences were not only formative for his intellectual development, but were also critical in shaping the very direction of modern science. The lessons he learned, both from his mentors and from his own experiences, would prove invaluable as he moved forward into the world of groundbreaking scientific discovery. Max Planck's time at the University of Munich marked the beginning of his deep intellectual journey, one that would ultimately lead him to reshape the very fabric of theoretical physics. Born into a family with a strong academic lineage, Planck's early education was shaped not only by his environment but also by the formative influences of the university system in Germany at the time. As a young man entering the academic world, Planck was eager to explore the scientific questions that intrigued him, and Munich provided the ideal setting for his academic growth. At the University of Munich, Planck began his formal education in the field of engineering, believing that it would allow him to apply scientific principles to practical problems. However, as he delved deeper into his studies, his natural curiosity and intellectual drive led him to question the nature of energy and matter in a more abstract way. This shift in focus toward theoretical physics wasn't an immediate decision, but one that came gradually as he encountered new ideas and gained exposure to the groundbreaking work of scientists like Hermann von Helmholtz, whose contributions to thermodynamics and the conservation of energy had already left a significant mark on the field. Planck's decision to move from engineering to physics was not merely a change in subject matter, but rather a turning point in his intellectual development. Physics, to him, represented a discipline that was concerned not only with the material world, but with uncovering the deeper, more fundamental laws that governed it. It was in Munich that Planck encountered the idea that physical systems, particularly those involving heat and energy, could be explained not just through mechanical processes but through the application of mathematical principles. This intellectual shift led him to dive into the works of prominent scientists such as Ludwig Boltzmann and James Clerk Maxwell, whose contributions to statistical mechanics and the theory of electromagnetism would play a significant role in Planck's future work. Despite his interest in theoretical physics, Planck's academic journey in Munich was not entirely smooth. As a young student, he struggled at times with the complexities of the subjects he was studying, particularly in the early years. The theoretical aspects of physics were not as straightforward as he had initially anticipated, and there were moments when he questioned whether he was on the right path. These doubts, however, did not deter him. Instead, they motivated him to delve deeper into the core principles of physics. It was during these early years in Munich that Planck began to develop the analytical and problem-solving skills that would serve him throughout his career. His ability to persevere through these intellectual challenges laid the groundwork for his later work, where he would tackle some of the most complex problems in theoretical physics. One of the key influences during Planck's time in Munich was his relationship with his professors. Though he studied under a number of distinguished scholars, it was particularly the guidance of Philipp von Jolly, a professor of physics, that had a profound impact on Planck's intellectual trajectory. Von Jolly was a well-respected physicist, known for his research in thermodynamics and his understanding of the laws of nature. Under von Jolly's tutelage, Planck became increasingly fascinated with the principles of energy conservation and the behavior of heat within physical systems. It was in the lectures and discussions with von Jolly that Planck first encountered the concept of entropy and the second law of thermodynamics concepts that would eventually influence his own groundbreaking work in the field of blackbody radiation. Vanjali's lectures on thermodynamics exposed Planck to the idea that the behavior of energy was not always intuitive and that physical systems often behaved in ways that could only be explained through the application of mathematical models. This realization had a lasting impact on Planck's scientific outlook. It was during these early years at Munich that Planck began to appreciate the importance of mathematics in the study of physics. He was not only drawn to the theoretical aspects of the subject, but also to the precision with which mathematical models could describe the physical world. This mathematical rigor would be a hallmark of Planck's work throughout his career, particularly in his development of the quantum theory. The combination of Planck's academic influences and his growing interest in the fundamental laws of physics led him to focus more intently on thermodynamics, particularly the study of heat and its transformation into other forms of energy. He began to realize that classical thermodynamics was not sufficient to explain certain phenomena, especially at the microscopic level. The existing laws of physics, although highly successful in many respects, had their limitations when it came to explaining the behavior of energy at the atomic scale. It was these limitations that prompted Planck to think more critically about the nature of energy and its interactions with matter. The realization that there were gaps in the current understanding of physics pushed Planck to explore new ideas, which ultimately led to the development of his theory of energy quantization. During this time in Munich, Planck also began to establish his own scientific methodology, which would set him apart from his contemporaries. While many physicists of the era adhered to established models and tried to refine them, Planck was not afraid to challenge accepted ideas. His willingness to question existing theories, combined with his meticulous approach to experimentation and mathematical analysis, would later become key components of his approach to physics. Planck's intellectual courage to step beyond the conventional wisdom of his time would serve him well in the years to come, especially as he tackled the most perplexing issues in quantum mechanics. By the time Planck completed his studies at the University of Munich, he had undergone a transformation from a young student with a broad interest in science to a focused and driven physicist dedicated to understanding the fundamental laws of nature. His academic journey had equipped him with the tools to address the complex challenges in physics, and he was ready to take the next step in his career. His decision to continue his studies at the University of Berlin marked a pivotal moment in his academic development, as it was here that he would encounter new ideas, meet influential mentors, and begin to work on the concepts that would eventually lead to his groundbreaking work in quantum theory. Planck's years at the University of Munich not only shaped his academic career, but also helped to forge the intellectual path that would define his legacy. His experiences in Munich allowed him to refine his understanding of thermodynamics, energy, and the principles of physics, while also developing the mathematical and analytical tools that would underpin his future work. More importantly, his time in Munich ignited a passion for science and discovery that would fuel his pursuit of knowledge throughout his life. Although he had not yet realized it, his early academic experiences would soon culminate in one of the most transformative discoveries in the history of science. As Planck's academic journey continued, it was clear that the foundation laid in Munich would play a central role in his future achievements. The intellectual climate of the time, combined with the guidance of his mentors and his own tireless work ethic, had prepared him to challenge existing theories and embark on a scientific path that would change the course of physics forever. His early years in Munich were not only formative in terms of his scientific knowledge, but also crucial in the development of his intellectual character, which would ultimately define his contributions to science. Max Planck's time at the University of Munich, though characterized by academic struggles and intellectual growth, played a pivotal role in shaping his journey towards becoming one of the most influential figures in the history of physics. His academic interests, particularly in the field of thermodynamics, would later lead him to a groundbreaking discovery that would change the course of science. Yet, it was during these early years that Planck honed the intellectual tools that would serve him throughout his career. The exposure to leading scientists and rigorous academic training in Munich was a critical part of this evolution, as it enabled Planck to develop his own understanding of physics, one that would be grounded in both theoretical rigor and experimental data. While Planck's transition from engineering to physics may seem abrupt, it was, in many ways, the result of an intellectual awakening. Physics presented him with a challenge that engineering could not offer: the challenge of understanding the fundamental laws governing the universe. Early on, Planck was captivated by the intricate relationship between energy and matter, particularly in the study of heat. His growing interest in thermodynamics was not merely a response to academic pressure, but rather a reflection of his profound curiosity about the natural world. Planck was deeply drawn to the study of energy, heat, and the laws that govern their behavior, and it was through this lens that he began to frame his academic questions. Planck's academic evolution in Munich was deeply influenced by the work of prominent physicists like Hermann von Helmholtz and Gustav Kirchhoff. Helmholtz, with his pioneering work on the conservation of energy, inspired Planck's understanding of how energy was not just a property of matter, but a fundamental aspect of nature that governed physical systems. Kirchhoff's work on the laws of radiation also had a significant impact on Planck, particularly in his understanding of the interaction between light and matter. These scientists' groundbreaking ideas, many of which were still in their infancy when Planck encountered them, set the stage for Planck's own future contributions. At the University of Munich, Planck's exposure to their ideas fueled his own intellectual pursuits. One of the major concepts that deeply influenced Planck was the second law of thermodynamics, which states that the total entropy of an isolated system always increases over time. This law, which was central to the study of heat and energy, became a cornerstone of Planck's research. It was during his time in Munich that he began to grapple with the limitations of classical thermodynamics and developed a deep desire to seek a more complete explanation of energy transformations. However, it was not simply the study of thermodynamics that consumed Planck. His intellectual curiosity extended to the broader fields of electromagnetism, statistical mechanics, and the interaction between heat and light. Despite the intellectual environment of Munich, Planck's academic journey was not without its personal struggles. As a young physicist, he faced numerous setbacks and moments of doubt. The complexity of the theories he encountered often led to moments of frustration. Planck, however, never let these challenges deter him. Instead, he grew from these intellectual struggles, using them as a way to refine his scientific thinking and approach. The constructive feedback he received from professors and peers alike, particularly Philip von Jolly, encouraged him to push the boundaries of his understanding. This intellectual resilience became a hallmark of Planck's career, and the perseverance he developed during these early academic years would help him tackle some of the most difficult problems in physics. Von Jolly's mentorship, in particular, was critical in shaping Planck's approach to scientific research. Von Jolly's expertise in thermodynamics and energy conservation allowed him to introduce Planck to the more advanced aspects of the field. It was under von Jolly's guidance that Planck first encountered the intricate relationships between energy and matter that would later inform his work on blackbody radiation. Von Jolly also encouraged Planck to approach his studies with precision and skepticism, teaching him the importance of thoroughly testing ideas and theories before accepting them. This rigorous approach to research became integral to Planck's future work, especially as he ventured into areas of physics where experimental evidence was scarce and theoretical models had to be developed from scratch. While his time in Munich was primarily focused on the study of thermodynamics, it was also here that Planck began to develop a more comprehensive understanding of the scientific method. He learned that science was not just about solving problems but also about asking the right questions. Planck realized that true scientific progress came not from accepting established theories, but from questioning them and seeking out new approaches that might lead to a deeper understanding of the natural world. This mentality became a defining feature of Planck's career and would later lead him to question the very foundation of classical physics, eventually paving the way for his revolutionary work in quantum mechanics. Another key aspect of Planck's academic development in Munich was his increasing appreciation for the mathematical nature of physics. Planck was drawn to the precision and elegance of mathematics as a tool for describing the natural world. His mathematical training, which was heavily influenced by the analytical traditions of German physics, provided him with the necessary tools to develop his own theoretical models. It was through this mathematical lens that Planck began to explore the fundamental laws of nature, and it would be this same approach that allowed him to develop the quantum theory. The years Planck spent in Munich were not only about acquiring knowledge, they were about shaping his intellectual identity. The lessons he learned, the challenges he faced, and the relationships he formed with his mentors were all integral to his academic and personal development. The intellectual environment of Munich provided Planck with the foundation upon which he would build his later contributions to physics. But it was not just the university's academic rigor that shaped him. It was also his personal drive and curiosity that pushed him to explore new areas of science and challenge established ideas. These qualities would come to define Planck's work in the years to come, as he set out to answer some of the most profound questions in physics. By the time Planck completed his studies at Munich, he had gained a deep understanding of the principles of thermodynamics and had begun to develop his own ideas about the nature of energy and heat. These early academic years shaped Planck's intellectual character, preparing him for the challenges ahead. Planck's ability to think critically, ask the right questions, and rigorously test his ideas laid the groundwork for the discoveries he would later make. His time at Munich had not only deepened his understanding of physics, but also ignited a passion for scientific inquiry that would drive him throughout his career. In many ways, Planck's experience at the University of Munich was a formative period in his development as a scientist. It was here that he was introduced to the core principles of physics that would inform his later work, and it was here that he first encountered the intellectual challenges that would shape his approach to science. Though he had not yet fully realized it, Planck's time in Munich was the beginning of a journey that would lead him to become one of the most influential scientists of the 20th century, a journey that would redefine the way we understand the nature of energy, matter, and the universe itself. Max Planck's time at the University of Berlin marked the most transformative period in his intellectual development, where his ideas evolved from being a student of physics to becoming a world-class physicist. The move from Munich to Berlin in 1879 was a monumental step, and it was during his years at the University of Berlin that Planck solidified his scientific principles, developed key theoretical frameworks, and began his most significant contributions to physics. Berlin, with its strong tradition of scientific inquiry, became a fertile ground for Planck to engage with the intellectual giants of his time, as well as a center of new scientific exploration. One of the most significant factors that contributed to Planck's academic growth during his time in Berlin was his exposure to the ideas of some of the greatest minds in physics, including Hermann von Helmholtz, Heinrich Hertz, and Gustav Kirchhoff. These scholars, who were pioneers in their respective fields, had an indelible influence on Planck's thinking. Helmholtz, with his work on the conservation of energy and his theory of physiological optics, inspired Planck's view of energy as a fundamental quantity that governed all physical processes. Kirchhoff, with his groundbreaking work on the theory of radiation and the relationship between temperature and the emission of radiation, helped deepen Planck's understanding of thermodynamics. However, it was particularly Heinrich Hertz's experiments on electromagnetic waves that sparked Planck's intellectual curiosity. Hertz's work demonstrated that energy could be understood and quantified in new and unprecedented ways. This exposure to advanced concepts and experimental findings not only deepened Planck's understanding of physical laws, but also encouraged him to think critically about the limitations of existing theories. In Berlin, Planck's scientific approach matured, and he began to grapple with the limitations of classical thermodynamics. His earlier work, which had been heavily influenced by his professors in Munich, began to take on a new dimension. Planck's deepening understanding of energy and the second law of thermodynamics led him to question the traditional explanations of heat and light. Classical physics, at the time, could not fully explain the behavior of energy at very small scales, especially when it came to phenomena like black-body radiation, where the classical theories fell short. This gap in understanding was one of the driving forces behind Planck's own revolutionary ideas. He realized that the laws governing the microscopic world could not simply be extensions of macroscopic laws, as classical physics assumed. The need for a new framework to understand atomic and subatomic behavior was becoming increasingly clear. This period in Berlin, where Planck interacted with groundbreaking work on energy and thermodynamics, laid the intellectual foundation for the ideas that would later culminate in the development of quantum theory. Planck's transition from student to professor, from an observer of physics to an active contributor to its development, was also a key feature of his time in Berlin. The University of Berlin offered Planck the opportunity to expand his academic horizon and immerse himself in both theoretical and experimental aspects of physics. It was in Berlin that he first had the chance to collaborate with other scientists and engage in the cutting-edge debates of the time. He was appointed to the chair of theoretical physics at the university in 1889, which allowed him to have a more direct influence on the scientific community. He began teaching his own students, passing on the knowledge and principles he had absorbed over the years. This transition was significant not only because of the professional recognition it afforded him, but also because it signified a shift in Planck's scientific maturity. Now, he wasn't just consuming knowledge from others. He was starting to build his own body of work, one that would later challenge and reshape established scientific paradigms. One of the most defining aspects of Planck's academic career in Berlin was his increasing focus on the study of black-body radiation. This particular topic was crucial in his journey towards the development of quantum theory. The problem of black-body radiation had been a significant challenge for physicists at the time, as classical physics could not explain the observed spectrum of radiation emitted by heated objects. Planck, with his deep understanding of thermodynamics and energy, sought to resolve this issue. He approached the problem by considering how the energy of oscillators in a black body cavity could be quantified, but with a key difference. He introduced the idea that energy could only be emitted or absorbed in discrete amounts, or quanta, rather than continuously. This was the fundamental insight that led to the birth of quantum theory. It was during his work on black-body radiation that Planck introduced the constant, which would later bear his name, the Planck constant, marking the first step toward the development of quantum mechanics. In his pursuit of an explanation for black-body radiation, Planck was forced to grapple with the conceptual challenges that arose from attempting to apply classical physics to phenomena at the atomic and molecular level. Classical thermodynamics, which was based on continuous variables, was ill-suited to explaining the observed phenomena at the microscopic scale. The introduction of quantization, which Planck initially viewed as a mathematical tool, turned out to be one of the most profound concepts in the history of physics. Planck's decision to introduce quantization wasn't motivated by a desire to challenge existing paradigms, but rather by the need to solve a very specific problem in the context of black-body radiation. He did not initially recognize the full implications of his discovery, but in retrospect, it marked the beginning of the quantum revolution. Planck's work in Berlin also involved a process of intellectual humility, and openness to new ideas. While he was a brilliant theorist, Planck did not consider himself to be above criticism or the established body of knowledge. His early exposure to the scientific community in Berlin taught him the value of constructive skepticism and the importance of refining ideas through debate and collaboration. This open-minded approach was integral to the development of his work on quantum theory, as Planck's ideas would later be challenged, refined, and extended by others, such as Albert Einstein and Niels Bohr. Planck, however, had the foresight to recognize the significance of his own work, even if he could not immediately grasp the full scope of its implications. In addition to his intellectual development, Planck's time in Berlin also involved significant personal growth. He had to navigate the challenges of balancing his scientific work with his responsibilities as a professor. Teaching at the University of Berlin exposed him to the next generation of scientists, and the experience of engaging with young, eager minds reinforced his own commitment to the scientific endeavor. His academic career was not just about personal advancement, but also about cultivating a new generation of physicists who would build upon his work. Planck's influence as a mentor and educator cannot be overstated. Many of his students went on to become important figures in their own right, contributing to the growth of quantum mechanics and physics as a whole. Through all of these experiences, Planck's intellectual maturity in Berlin helped shape the man who would eventually challenge classical physics with his development of quantum theory. It was in Berlin that Planck formulated the ideas that would lead him to create the first quantum theory, revolutionizing our understanding of energy, matter, and the universe itself. The city, with its vibrant scientific community and its exposure to cutting-edge ideas, provided the ideal environment for Planck to develop his thinking and embark on the path that would define his legacy. His time in Berlin wasn't just about absorbing the work of others, it was about synthesizing new ideas, challenging established beliefs, and forging a new direction for science. Max Planck's years at the University of Berlin were marked by a period of intense scientific exploration, intellectual growth, and groundbreaking work that would shape the future of physics. By the time he arrived in Berlin, Planck had already established himself as a promising young physicist, but it was in this intellectual hub of Europe that his ideas would mature into revolutionary concepts that would alter the trajectory of science. Berlin was the center of a thriving scientific community, and for Planck, this environment would offer a wealth of inspiration, collaboration, and intellectual exchange. The years he spent in Berlin were not just formative in terms of his academic growth, but they also provided the foundation for his most famous contributions to physics, particularly the birth of quantum theory. Upon his arrival in Berlin, Planck was thrust into an intellectual ecosystem where the foremost questions in physics were being discussed and debated. Berlin was home to a number of distinguished scientists, including Hermann von Helmholtz, Gustav Kirchhoff, and Heinrich Hertz, whose works would heavily influence Planck's own thinking. Helmholtz's ideas on energy conservation, Kirchhoff's contributions to the laws of radiation, and Hertz's work on electromagnetic waves all played pivotal roles in shaping Planck's scientific worldview. The university's intellectual vibrancy encouraged Planck to engage more deeply with the great scientific challenges of his time, most notably the problem of black-body radiation. The issue of black-body radiation had baffled physicists for decades. Classical physics, as it stood, could not explain the observed radiation spectrum emitted by heated objects. The prevailing theories based on Maxwell's equations and the laws of thermodynamics predicted infinite energy emission at short wavelengths, which was known as the ultraviolet catastrophe. Planck, grappling with the limitations of classical physics, sought a solution. At the time, there was a widespread belief in the continuity of energy, meaning energy could be exchanged in any amount. However, Planck, driven by both necessity and intuition, proposed a groundbreaking idea, that energy could only be exchanged in discrete quantities, which he called quanta. This insight would form the foundation of quantum theory. Planck's idea came not as a philosophical breakthrough, but as a mathematical necessity. To resolve the problem of blackbody radiation, Planck proposed that the energy of oscillators in a blackbody cavity could only take discrete values proportional to the frequency of the radiation. This was captured in his famous formula, where energy was quantized by the factor E equals h nu, with Ha representing the Planck constant and nu being the frequency of radiation. Initially, Planck saw this quantization as a mathematical tool, a way to fit the experimental data without fully understanding the profound implications of what he had discovered. However, this idea would become the cornerstone of quantum mechanics, forever changing the way we understood the micro world. Planck's introduction of the quantization of energy was initially met with skepticism. The scientific community was deeply entrenched in classical notions of continuous energy, and Planck's revolutionary suggestion challenged the very foundations of physics. Planck himself did not immediately grasp the full significance of his work, as he was reluctant to let go of the classical framework. Yet, the success of his theory in explaining blackbody radiation proved its value. The Planck constant, which emerged as a central element of his equation, became one of the most important constants in physics, cementing his place as one of the founders of quantum theory. While Planck's work on blackbody radiation was his most famous contribution, his time in Berlin was also defined by his broader engagement with the scientific community. His appointment to the chair of theoretical physics at the University of Berlin in 1889 marked the beginning of a new phase in his career. Now a professor, Planck was responsible for mentoring the next generation of physicists. His role as a teacher was significant not only for his students, but for Planck himself, as teaching pushed him to refine his ideas and engage with younger, eager minds. His approach to teaching was rigorous and deeply analytical, and his students were fortunate to benefit from his vast knowledge of physics, as well as his philosophical approach to scientific inquiry. One of Planck's most important contributions during this period was his role in shaping the scientific culture at Berlin. Berlin was home to the German Physical Society, and Planck played a central role in organizing its meetings and discussions. These gatherings were often a focal point for intellectual debate, and Planck's ability to facilitate and engage in discussions about emerging scientific ideas helped shape the direction of physics during this period. It was at these meetings that many of the most important discussions in theoretical physics took place, and Planck's presence ensured that his own ideas were given serious consideration. Planck's work was also increasingly recognized beyond the borders of Germany. He began to correspond with some of the greatest scientific minds of the time, including Albert Einstein, who would later build on Planck's ideas to develop the theory of relativity. The relationship between the two scientists was based on mutual respect and intellectual curiosity. Planck recognized the importance of Einstein's work and, in turn, Einstein revered Planck as a mentor. Their correspondence and collaboration over the years would help establish the foundations for modern physics, with Planck's quantization of energy and Einstein's theory of relativity serving as two of the most important pillars of 20th century physics. During his years in Berlin, Planck's intellectual influence also extended beyond the field of physics. His work on the mathematical formulation of thermodynamics, his advocacy for a more rigorous approach to scientific inquiry, and his ability to synthesize diverse scientific ideas helped shape the intellectual climate of the time. Planck's scientific philosophy, grounded in the principles of rigorous experimentation, logical reasoning, and mathematical precision, resonated deeply with his contemporaries. Planck was not just a theoretical physicist, he was also a thinker who sought to understand the fundamental principles that governed the universe. His ability to combine theoretical work with practical experimentation was one of the reasons he became such an influential figure in the scientific community. The scientific climate of Berlin, with its focus on collaborative research and intellectual exchange, was integral to Planck's own development as a physicist. Berlin was a city that fostered innovation and dialogue, and it provided Planck with the opportunity to refine his ideas and confront the scientific challenges of the day. His work in Berlin was not just a personal academic journey, but part of a broader intellectual movement that sought to understand the nature of reality on the most fundamental level. Planck's contributions during this period were not limited to his groundbreaking work on blackbody radiation. They extended to the development of the quantum theory, the role of mathematics in physics, and the shaping of a scientific culture that valued both theoretical and experimental approaches to scientific inquiry. By the time Planck left Berlin in the early 1900s, he had already established himself as a leading figure in the world of physics. His work on blackbody radiation, the development of quantum theory, and his contributions to the scientific community in Berlin helped define the direction of modern physics. However, his intellectual journey was far from over. In many ways, his work in Berlin was just the beginning of his lasting impact on the scientific world. His time in Berlin set the stage for the next phase of his career, during which he would continue to challenge the assumptions of classical physics and lead the way toward a new understanding of the quantum world. His legacy, which was firmly rooted in his time in Berlin, would continue to shape the future of physics for generations to come. Max Planck's journey, from student to professor, was not just a personal academic evolution, but a pivotal transformation in the history of science itself. The University of Berlin, a thriving epicenter of intellectual exchange, provided Planck the environment he needed to refine his theoretical framework and begin his revolutionary contributions to physics. His academic career in Berlin, particularly in the late 19th century, was defined by his interaction with the prevailing scientific challenges of the time, his engagement with the intellectual giants of the era, and his development of a groundbreaking theory that would lead to the birth of quantum mechanics. When Planck arrived in Berlin, it was at a time when classical physics was struggling to explain certain phenomena, particularly those related to radiation. The classical laws of thermodynamics and electromagnetism failed to accurately describe the radiation emitted by heated objects, a problem known as blackbody radiation. This issue had been a significant point of contention in the scientific community, and despite various efforts, no satisfactory explanation had been found. Classical physics, governed by the laws of continuous energy flow, could not explain the discrete behavior of radiation, particularly at the atomic scale. It was against this backdrop that Planck embarked on his journey to understand energy in a new way. Planck's work was influenced heavily by his engagement with the intellectual and experimental advancements of his time. The University of Berlin was home to prominent scientists like Hermann von Helmholtz and Heinrich Hertz, whose research laid the groundwork for Planck's own thinking. Helmholtz's work on energy conservation and the laws of thermodynamics, and Hertz's experiments with electromagnetic waves, exposed Planck to the fundamental principles that governed much of the scientific inquiry of the day. Yet, despite these monumental influences, the prevailing scientific theories were still limited by their inability to explain the quantum phenomena that Planck would soon uncover. Planck's intellectual curiosity pushed him to seek a new way to understand the relationship between energy and matter, one that would eventually dissolve the limitations of classical thermodynamics. The breakthrough that Planck introduced was the idea of quantization. This concept, which emerged from his work on blackbody radiation, suggested that energy could only exist in discrete quantities rather than in a continuous flow as was traditionally thought. This revolutionary idea was not born from an abstract theory, but as a necessary mathematical solution to explain the observed radiation spectrum. Planck introduced the notion that oscillators in a blackbody cavity could only absorb or emit energy in specific amounts, or quanta, and the energy of these oscillators was directly proportional to their frequency. This insight, now encapsulated in the famous Planck equation, laid the foundation for quantum theory. At first, Planck did not fully appreciate the magnitude of his discovery. He introduced quantization as a mathematical construct to solve a particular problem in radiation theory, not as a radical departure from classical physics. However, the implications of this discovery soon became clear. Planck's introduction of the constant, now known as the Planck constant, provided the necessary tool to explain black-body radiation, and it became one of the most significant constants in physics. Although Planck initially believed that his work was merely a mathematical convenience, his theory would soon open the door for other scientists, like Albert Einstein and Niels Bohr, to further develop the quantum revolution. Planck's academic role also expanded during his years in Berlin, where he became a professor of theoretical physics. In this capacity, he mentored many students who would go on to make their own significant contributions to the field of physics. Planck's teaching philosophy was rigorous, emphasizing both the theoretical and experimental aspects of physics. He believed that students should not just absorb knowledge, but engage with the material, ask questions, and challenge existing theories. His teaching, deeply rooted in his scientific methodology, encouraged a generation of physicists to think critically about the fundamental principles that govern the natural world. As a professor at the University of Berlin, Planck was not only a mentor to students but an active participant in the larger scientific dialogue of his time. His involvement in the German Physical Society and his interactions with other scientists helped shape the intellectual environment in which modern physics began to take form. These interactions, both collaborative and challenging, played a crucial role in refining Planck's own ideas and advancing his work. His time in Berlin was not just marked by academic success, but by his ability to influence the trajectory of scientific thought, setting the stage for the quantum mechanics that would dominate 20th century physics. Max Planck's academic journey in Berlin was crucial not only for his personal development, but also for the broader trajectory of physics. It was here that he made the transition from a promising student to a leading figure in the scientific community. His time at the University of Berlin exposed him to the cutting-edge developments of the time, introduced him to key scientific figures, and ultimately led to his revolutionary contributions to the field of quantum mechanics. When Planck moved to Berlin, the city was a vibrant hub of intellectual exchange, attracting some of the brightest minds in science. The University of Berlin, with its rich tradition of scientific excellence, became the ideal environment for him to deepen his understanding of physics. Planck's exposure to the work of scientists like Hermann von Helmholtz, Heinrich Hertz, and Gustav Kirchhoff was crucial in shaping his scientific perspective. These figures, who were pioneers in thermodynamics, electromagnetism, and radiation theory, significantly influenced Planck's thinking. The rigorous academic atmosphere of Berlin provided Planck with the intellectual foundation necessary for his later groundbreaking work. At the University of Berlin, Planck began to focus more intensively on the pressing scientific challenges of the time. One of the most significant issues that troubled physicists was the problem of black-body radiation. Classical physics, at the time, struggled to explain the observed spectrum of radiation emitted by heated objects, especially at shorter wavelengths. The ultraviolet catastrophe, as it was known, predicted an infinite amount of radiation at high frequencies, which was at odds with experimental observations. This discrepancy called for a new theory, and it was this challenge that Planck would address. In his effort to solve the problem of black-body radiation, Planck made a discovery that would change the course of physics. He proposed that energy was not emitted or absorbed in continuous amounts, but in discrete units, or quanta. Planck's introduction of quantization was a purely mathematical solution to the problem at hand, as he sought to reconcile the experimental data with theoretical expectations. Initially, Planck believed that this quantization was merely a tool to fit the data, not realizing that he had uncovered a principle that would become the cornerstone of quantum theory. His introduction of the Planck constant, which related the energy of a quantum to its frequency, would later become one of the most important constants in modern physics. While Planck's work on black-body radiation solved an immediate problem in thermodynamics, it also laid the groundwork for the quantum revolution. His idea that energy is quantized was groundbreaking, but it took several years before its full implications were understood. Planck himself did not initially grasp the revolutionary nature of his discovery. However, as the work of other physicists, particularly Albert Einstein and Niels Bohr, built upon Planck's insights, it became clear that quantization was not just a mathematical trick, but a fundamental principle of the universe. Planck's work opened the door to the development of quantum mechanics, a field that would revolutionize our understanding of the atomic and subatomic worlds. As a professor, Planck also played a significant role in shaping the next generation of physicists. His influence extended beyond his own research, as he mentored students who would go on to make their own major contributions to science. Planck's approach to teaching emphasized the importance of both theoretical understanding and practical experimentation. He encouraged his students to think critically and to challenge existing ideas. His academic rigor and commitment to the scientific method helped foster an environment of intellectual curiosity that would inspire future generations of physicists. Planck's dedication to teaching was matched only by his passion for discovery, and his ability to inspire those around him made him a respected figure in the scientific community. In Berlin, Planck also became more involved in the scientific community through his participation in various scientific organizations, including the German Physical Society. These interactions with other leading scientists provided Planck with the opportunity to exchange ideas and collaborate on solving some of the most pressing issues in physics. His work on black-body radiation, in particular, became a focal point of scientific discussion and helped establish him as a leading figure in the field. Planck's time in Berlin was marked by both individual achievements and collaborative efforts as he worked to push the boundaries of scientific knowledge. Planck's years in Berlin were not only about scientific discovery, but also about intellectual growth and influence. His time at the University of Berlin allowed him to hone his skills as a physicist, to engage with the leading scientific minds of the time, and to make discoveries that would reshape the world of physics. The city provided the intellectual and professional environment Planck needed to develop his ideas and contribute to the scientific advancements that would define the 20th century. His time in Berlin was a period of personal and professional transformation, one that set the stage for the groundbreaking contributions that would follow. Max Planck's academic journey in Berlin was instrumental in shaping his scientific career and defining his legacy in the field of physics. During his time at the University of Berlin, Planck made significant strides in both his personal development and his contributions to the scientific community. The intellectual environment in Berlin, combined with Planck's own determination and curiosity, fostered the development of some of the most important ideas in modern physics, which would later become the foundation for the quantum revolution. When Planck arrived in Berlin in 1879, he entered a city that was at the heart of scientific advancement in Europe. Berlin was home to some of the most respected minds of the era, including Hermann von Helmholtz, Heinrich Hertz, and Gustav Kirchhoff. These physicists, along with others at the University of Berlin, played an important role in shaping Planck's understanding of physics and introducing him to the most pressing scientific challenges of the time. The intellectual atmosphere in Berlin encouraged critical thinking, collaboration, and engagement with the latest developments in physics, which had a profound influence on Planck's later work. The city provided him with the perfect setting to refine his own theories and to contribute to the broader scientific conversation. It was during this time in Berlin that Planck focused on solving one of the most perplexing problems in physics, the issue of black-body radiation. Classical physics, at the time, could not explain the observed behavior of radiation emitted by heated objects. The laws of thermodynamics, along with Maxwell's equations of electromagnetism, predicted that radiation should increase infinitely at high frequencies, a phenomenon known as the ultraviolet catastrophe. This contradiction between theory and experiment was one of the major unresolved problems in physics, and Planck, armed with his deep understanding of thermodynamics and radiation, sought to find a solution. Planck's breakthrough came when he proposed that energy is not emitted or absorbed continuously, but in discrete quantities, or quanta. This idea, which came to him as a result of his work on black-body radiation, marked the beginning of the quantum theory. Initially, Planck introduced this quantization of energy as a mathematical tool to fit experimental data, not realizing the full significance of his discovery. However, as the implications of quantization became clear in the years that followed, it became apparent that this principle would reshape the future of physics. The idea that energy is quantized would later become a cornerstone of quantum mechanics, and the Planck constant would become one of the most important constants in the field. Planck's work on blackbody radiation was not just a theoretical triumph. It also illustrated his methodical and rigorous approach to solving scientific problems. He did not take existing theories for granted, but instead sought to refine and improve them. His willingness to question accepted ideas and to introduce novel concepts allowed him to address the shortcomings of classical physics. His approach to scientific inquiry was deeply rooted in empirical evidence, and he placed great importance on aligning theoretical models with experimental data. This methodical approach would later serve him well as he continued to contribute to the scientific community, particularly as his ideas were further developed by other physicists such as Albert Einstein and Niels Bohr. Planck's role in Berlin was not limited to his individual research. As a professor at the University of Berlin, he became an important mentor and educator. His rigorous teaching style encouraged students to think critically, challenge established ideas, and develop a deep understanding of physics. Planck's academic influence extended beyond his immediate research as he shaped the next generation of physicists. He was not only a scientist working in isolation but also an active participant in the broader scientific community. His involvement with the German Physical Society, where he collaborated with other prominent physicists and contributed to intellectual discussions, further solidified his standing as one of the leading figures in theoretical physics. During his time in Berlin, Planck's work became increasingly recognized by the international scientific community. His ideas on energy quantization and blackbody radiation were pivotal in the development of quantum theory, and his participation in global scientific dialogues contributed to the widespread acceptance of his ideas. The intellectual environment of Berlin, with its emphasis on collaboration and the exchange of ideas, played a significant role in helping Planck develop and refine his theories. The city's rich scientific heritage, combined with the presence of numerous distinguished scientists, helped foster the development of quantum mechanics, with Planck at the helm of this revolution in physics. In addition to his professional success, Planck's time in Berlin was also marked by personal challenges and growth. His intellectual journey was not always smooth. He faced periods of doubt and uncertainty, especially as he navigated the complexities of blackbody radiation and quantum theory. However, these struggles were integral to his development as a scientist. They taught him resilience and the importance of persistence in the face of scientific challenges. Planck's ability to overcome these obstacles and make a groundbreaking discovery in the face of adversity is a testament to his intellectual courage and commitment to scientific progress. The legacy of Planck's time in Berlin extends far beyond his personal achievements. His work laid the foundation for the development of quantum mechanics and altered the course of physics in the 20th century. Planck's introduction of the concept of quantization, his rigorous scientific method, and his ability to challenge established theories set the stage for the quantum revolution. His time in Berlin, marked by both personal and professional growth, provided the environment and intellectual stimulus necessary for him to make the discoveries that would change the way we understand the universe. Max Planck's intellectual journey through Berlin shaped his transformation from a student of physics into one of its most influential pioneers. Berlin, at the time, was a dynamic center of scientific thought, providing Planck with the opportunity to engage deeply with the ongoing advancements in thermodynamics and electromagnetism. The university environment, rich in academic rigor and intellectual exchange, played a significant role in nurturing his scientific ideas and pushing him toward the discovery that would revolutionize physics. Planck's exposure to the work of leading scientists such as Hermann von Helmholtz and Heinrich Hertz, combined with the university's intellectual culture, deeply influenced his scientific thinking and provided him the intellectual tools necessary to tackle some of the era's most pressing scientific problems. At the University of Berlin, Planck found himself grappling with the well-known issue of blackbody radiation. Classical physics, particularly through Maxwell's equations, was unable to explain the radiation emitted by a heated object. This problem, known as the ultraviolet catastrophe, suggested that an object would emit infinite energy as it approached short wavelengths, which clearly contradicted experimental observations. The inability of classical physics to account for these observations led Planck to search for an entirely new theoretical framework. His deep understanding of thermodynamics and his engagement with the works of Kirchhoff, Helmholtz, and others helped Planck develop a new approach that would eventually challenge existing theories. Planck's solution to the blackbody radiation problem was revolutionary. He proposed that energy is not emitted or absorbed continuously, but in discrete packets, or quanta. This was the first introduction of the concept of quantization, a concept that would form the cornerstone of quantum theory. Initially, Planck introduced quantization as a mere mathematical tool, a way to fit the experimental data with the theoretical predictions, but he did not fully recognize the broad implications of this discovery. The formula that Planck developed to explain the spectrum of blackbody radiation, which included the Planck constant, would later become one of the most fundamental constants in physics, shaping the field of quantum mechanics in ways Planck had not yet envisioned. The introduction of quantization by Planck was not an arbitrary decision, but one rooted in the scientific rigor of his training. Planck was not willing to accept the failures of classical physics. Instead, he sought a way to reconcile theory with experimental evidence. His work on blackbody radiation highlighted his deep commitment to the scientific method, where empirical evidence guided theoretical development. Planck's ability to approach the problem with a fresh perspective, while still relying on a solid foundation of thermodynamics and electromagnetism, was crucial to his success. This intellectual perseverance would later make him one of the key figures in the development of quantum mechanics. Another important aspect of Planck's time in Berlin was his interaction with his mentors and colleagues. Planck's relationship with Hermann von Helmholtz was especially significant. Helmholtz was a leading figure in thermodynamics and energy conservation, and his work provided a conceptual framework that was instrumental in shaping Planck's understanding of energy. Planck also interacted with other key physicists, like Gustav Kirchhoff, whose laws of radiation played a crucial role in the formulation of Planck's own theories. These collaborations and intellectual exchanges helped Planck refine his ideas and deepen his understanding of the physical world. The intellectual environment in Berlin, with its emphasis on rigorous inquiry and debate, was crucial in fostering Planck's intellectual maturity. Planck's appointment as a professor at the University of Berlin in 1889 marked a significant milestone in his career. As a professor, Planck not only conducted his own research, but also mentored a generation of physicists who would go on to make their own contributions to science. His pedagogical approach emphasized the importance of both theoretical understanding and practical experimentation, encouraging his students to think critically about the scientific questions they faced. Planck's role as an educator was not just about imparting knowledge, but about inspiring the next generation of scientists to pursue their own intellectual journeys, much like he had done throughout his academic career. Planck's work in Berlin also laid the foundation for future scientific collaboration. His groundbreaking work on black-body radiation would later be expanded upon by other great physicists, including Albert Einstein. While Planck's initial work introduced the concept of energy quanta, it was Einstein who used this idea to explain the photoelectric effect, for which he would win the Nobel Prize. This collaboration, both direct and indirect, demonstrated the collaborative nature of scientific discovery. Planck's contributions were crucial in setting the stage for the broader quantum revolution that would take place in the early 20th century. Max Planck's time in Berlin was a period of profound intellectual growth and scientific achievement. His work on black-body radiation, which introduced the concept of energy quantization, laid the groundwork for the quantum mechanics that would dominate the 20th century. His interactions with other leading scientists and his role as an educator helped shape the direction of physics during this period. Planck's work not only solved one of the most pressing problems in thermodynamics, but also opened the door to a new era of scientific inquiry. His intellectual legacy continues to influence the way we understand the universe, and his work in Berlin was a crucial chapter in the history of physics.